Welcome to our project. This is a project where we try to look at how to use the causal AI to try to understand the human mobility behavior using the trajectory data. The trajectory data is basically you record like where and when the people appears when they travel. It can be like from the mobile phone data, can be from the smartcard data, that is when we travel using public transport. My name is Jenny Ma. I'm an assistant professor in transport at KTH, and also the co-PI. Liam Solos is an assistant professor in mathematics, also at KTH. This is our project team. We have one postdoc and also one PhD student participate like in this project. A bit about the background. So basically now like our cities face lots of challenges, the congestions, and also the disruption, disasters. To understand the human mobility behavior dynamics is the fundamental to try to come out with the preparedness or response policies to address certain challenges. There's like two research like societies in this area. So one is in transportation. It's basically we usually use the survey data to try to understand why people make certain choices under certain conditions. There's also like computer science society make use of this big data to try to model the job patterns for the people under different conditions. So basically we focus on the same problem, but we use different data sets and also we use different approaches. There's a convergent need for these two societies. This data and AI, they are key technology enablers, right? And also it's very common like for this mobile, cyber, physical, social systems that we get more and more trajectory data. So the common like AI, they are quite strong in the predictions. But the question is like whether we can develop some predictive AI for what if questions. This is like what this product try to look at. Since like we focus on this behavior dynamics, we formulate this behavior learning problem as a causal reinforcement learning problem. So it basically combines the reinforcement learning method, which is efficiently learning from the trajectories, and also the causal inference model, which is strong at the reasoning, and also like for the generalization capabilities on the different situations. So if you look at this figure, basically we structure this model using the scan network. We have this generator, we have the discriminator. So basically we would like to train a generator that can mimic the human like travel behavior trajectories that we prepared from the real world. Differently from the traditional like reinforcement learning, we replace this neural net-based generator to this causal generator. That means like we use the causal graph to replace the policy functions in this generator. And then we use the scan network to try to calibrate the parameters in the causal graph. And in the end, basically we will like test like our algorithm in different cases, then try to derive some insights that we can use in practice. We have a 3-work package, and for the past several months, and basically we focus on the work package 1 to try to prepare these mobility behavior trajectories, which we would like to have this big data with this small like survey data combined up, and then we can somehow like for all the trips, we try to impute what are the traveler's characteristics and also the trip conduct. For the case study, basically we select a policy intervention that was implemented in Hong Kong. This is like called like early bird promotion. It is one of the incentive program to try to influence people to travel in the off-peak hours in the morning. It was implemented in September 2014. So basically, it provides like 25% fare discount for the selected stations, which is circled using the dashed line in the right figure. And also it has a selected time period. It's 7:15 to 8:15, which is off-peak hour in the morning. Basically, it means if people exit one of the station in this selected area between 7:15 to 8:15, they can receive this 25% discount. And then they update this program to 35% discount with more stations in 2019, based on some of the analysis that we had. And the objective for this program is basically to try to reduce some of the flows on the congested links, which are represented using the red arrows. The source of the data that we have is mainly about the smartcard data, which is 2 years. It has both tap in and tap out information recorded. And then we have the train movement data. Basically, it shows where the train, when the train is. And also develop this network performance model and also choice estimation model solely based on the smartcard data. So I can infer what are the routes the people has choose to use, and also what are the congestion levels in different stations and different lines, and also on different trains. So the right table basically shows the information that we prepared for this product. I categorized them into different groups. One is the individual information. I know their anonymous ID. This ID is also consistent across different days in the product. And we also have the individual attribute, which is imputed by combining with the survey data. We know what are the people status, whether they are adult and the students, people. Also, we know their home and work locations. For the trip information, when the trip happens, the date, and also what the trip purpose, for shopping, work, or others. And for the travel behavior, how frequent they travel, what the depart time for the morning travels, their origin station, destination station, and also route they used. For the service, basically other factors influence people's behavior choices, like the crowding at the stations, on the train load, the left behind on stations, in-vehicle travel time, transfer times, and the fare cost. So after we prepare the data set, we have done some statistical analysis to try to understand preliminary what are the behavior change patterns. So the first step, we develop some models to try to identify the adopters, basically who are the passengers actually change their behavior because of this incentive. And then after we identify the adopters, and we look at their adoption patterns in an aggregated way, from both short-term and long-term perspective. And also we try to model their adoption behavior to try to understand what are the important factors actually influence their adoption choices. So this result shows the distribution of the exit time of the adopters before promotion, which is shown in this blue line, and also after promotion, that is shown in this orange line. This shaded area is basically the promotion time period from 7:15 to 8:15. So we can see that it is very obvious the change of these peaks of these adopters before and after promotion. But one thing to mention is that the right group of people who shifted from the peak hour to the off-peak hour is what we expect for this incentive. Right? What we try to discourage is the people who already travel in the very early and then they shift to this promotion period. They do not really contribute to the reduction of the traffic on the congested links, but they still enjoy the discount, which is not expected. And also the peak difference is around 15 minutes. And if you look at this figure, basically in average, we count this 2.5% of the people actually shift their peak travels to the off-peak. And then if you look at how much time actually they change their habitual depart time, is mostly around 15 to 30 minutes, right? So for example, if you look at the left group of the people, so basically for this group, their exit time before promotion is 8:15 to 8:30. And then if you look at how many people shift to 8 to 8:15 after promotion, that is 2.8%. And then there's very like a steep decrease of the people who will shift their depart time to 7:45 to 8, right? That means that they need to shift 30 minutes to that period. So the same thing we can see, look at like from other groups as well. And if you look at this longitudinal response of these users, if you look at this heat map, so basically if column is the behavior in each month, and each row is basically each user. And then we stack those users based on like the first attrition time. The attrition time means like they adopt the incentive, they change the behavior, but after several months, actually they reverse back to what they behaved before. So we can see like in the bottom, basically they are all blue. That means like those people change their behavior and then they continue the changed behavior until the studied period is like 2 years. And then for the people in the middle, we can see some like a periodical shift back and forth. It's basically also corresponding to the holidays, which is as expected. In the upper block, basically we can see like the people mostly they try like 2 months or 3 months or like several months, and then they decide not to continue this change. And the bottom figure basically shows like there's a 65% of people actually sustain the behavior in 2 years. And the sharp decrease actually happens in the 3rd month. We also like develop this statistical model, which is called the discrete trust model, to try to understand for the adopters and non-adopters what are the factors influence. And basically from this table, we can see that like for the user, if it has a high scalability, has a low minimum displacement time, this is basically shows the inconvenience, basically how much time they need to change in order to get the discount. And if they have the higher FLCVs, basically they are more likely to adopt this incentive and also change their behaviors. And we can also see like there's some like different behaviors depending on like where they work. And also like in general, like people hesitate to shift because this constant values is negative. So just to summarize, so we perform this data-driven analysis, which is more like statistical analysis and modeling. So we try to understand like what are the important factors basically influence the behavior changes under policy interventions. And it can have like good implications for us is that like we need to target the effective users, like basically whose behavior change really contribute to the system objectives. But at the same time, we would like to target the price-sensitive users and also sustainable users so that we can maximize our investment benefit. So the next step is basically we would like to look at the causal graph discovery to see whether we can get the same result as what we can get from the statistical model. Thanks very much.